Welcome to the world of digital electronics, where logic meets innovation to power modern technology. In digital electronics, a comparison circuit, also known as a comparator, compares two binary numbers and determines their relationship. It tells us whether A is greater than B, A is less than B, or A is equal to B. These circuits are fundamental building blocks in digital systems. Inside ALUs, comparators help make arithmetic decisions. In CPUs, they support conditional branching instructions. In DSP systems, they assist with magnitude detection and signal evaluation. And within control units, they enable operations like sorting, address checking, and priority decisions. Without comparators, processors cannot make logical decisions. Now let's understand the simplest form of a comparator, the one-bit binary comparator. It has two inputs, A and B, each just one bit, either 0 or 1. It produces three outputs, G, which indicates A is greater than B, E, which indicates A is equal to B, L, which indicates A is less than B. Now let's analyze the truth table. When A is 0 and B is 0, both values are equal, so A equals B becomes 1. When A is 0 and B is 1, A is less than B, so the A less than B output becomes 1. When A is 1 and B is 0, A is greater than B, so the A greater than B output becomes 1. Finally, when both are 1, again they are equal, so the equality output becomes 1. Notice an important rule. At any time, only one output is high. This ensures clear, unambiguous comparison. Let's convert the one-bit comparator truth table into Boolean expressions and then into a gate-level circuit. First, for A greater than B, A must be 1 and B must be 0. So the expression is G equals A times B. Next, for A less than B, A must be 0 and B must be 1. So the expression is L equals A times B. And for A equal to B, either both are 0 or both are 1. That condition is an XNOR, so E equals A XNOR B. Now look at the circuit diagram. We generate B prime using an inverter and feed A and B prime into an AND gate that produces G. Similarly, we generate A prime using another inverter and feed A prime and B into an AND gate that produces L. Finally, the equality output E is created using an XNOR behavior, meaning it goes high only when inputs match. Let's extend the concept to a 2-bit comparator, comparing A1, A0 with B1, B0. The most important rule is compare the most significant bit first. Step 1, compare A1 with B1. If A1 is greater than B1, then the entire number A is greater. If A1 is less than B1, then A is smaller. Only when the MSBs are equal do we move to the next step. Compare the LSBs, A0 and B0. Now let's translate that into logic. For equality, both bit positions must match. So A equals B equals A1 XNOR B1 and A0 XNOR B0. For A greater than B, there are two possibilities. Either A1 is greater than B1 directly, or the MSBs are equal and A0 is greater than B0. Similarly, A less than B happens when A1 is less than B1, or the MSBs are equal and A0 is less than B0. So notice the structure. MSB decides first. LSB matters only when MSBs are equal. This hierarchical comparison principle is exactly how larger 4-bit, 8-bit, and 32-bit comparators inside ALUs are designed. Now let's analyze the complete gate-level implementation of a 2-bit comparator. We are comparing two 2-bit numbers, A1 bar and B1 bar. At the top, you can see inverters generating the complements of each input, A1 bar, A0 bar, B1 bar, and B0 bar. These are required to build the greater than and less than conditions. Let's start with the A less than B output. There are two possible cases. First, if A1 is less than B1 directly, that is A1 bar and B1. Second, if the MSBs are equal and A0 is less than B0. These product terms are generated using AND gates, and then combined using an OR gate to produce A less than B. Now look at the equality block in the middle. Equality requires both bits to match. So, A1 XNOR B1 generates MSB equality. A0 XNOR B0 generates LSB equality. These two outputs are ANDed together to produce A equals B. Finally, the A greater than B output at the bottom follows the same hierarchy. Either A1 and B1 bar, or MSBs are equal and A0 and B0 bar. Notice the structured architecture. Top section, less than logic. Middle section, equality logic. Bottom section, greater than logic. This layered MSB priority design is exactly how scalable comparators are built inside ALUs and processors. Let's generalize the idea to an n-bit comparator, meaning we compare two numbers with any number of bits. The key rule stays the same. We always compare from MSB to LSB. Why MSB first? Because the MSB has the highest weight. So the first bit position where A and B are different immediately decides the final result. If at that first mismatch, A's bit is 1 and B's bit is 0, then A is greater. If A's bit is 0 and B's bit is 1, then A is smaller. And if every bit matches all the way to the LSB, then A equals B. Now let's look at the hardware structure. For equality, we use a chain of XNOR gates. Each XNOR checks if a pair of bits are equal. Then we combine all those XNOR outputs using AND logic, so equality becomes 1 only when all bits match. For magnitude, greater than or less than, we build a priority-style logic using OR AND structures. This logic ensures MSB mismatch dominates. And lower bits matter only when higher bits are equal. So the big idea is simple. XNOR plus AND gives equality, and priority OR AND logic gives greater/less. This is the exact concept used in real processors, whether it's a 4-bit comparator or a full 32-bit ALU compare instruction. Let's move from theory to a real hardware implementation. The 74HC85, a 4-bit magnitude comparator IC. This chip compares two 4-bit numbers, A3 to A0 and B3 to B0, and directly produces three outputs, A greater than B, A equal to B, and A less than B. Internally, it performs MSB first comparison, exactly like our generalized n-bit concept. The highest bit is checked first, and lower bits are evaluated only if higher bits are equal. One powerful feature of the 74HC85 is its cascade capability. Notice the expansion inputs. These allow multiple comparators to be connected together. On the right side, you can see two 74HC85 ICs connected to form an 8-bit comparator. Here's how it works. The lower 4-bit comparator handles the least significant bits. Its outputs feed into the expansion inputs, of the higher 4-bit comparator. This ensures priority logic. The higher-order comparator dominates unless the upper bits are equal, in which case the lower comparator result is used. This cascading mechanism allows us to build 8-bit, 16-bit, or even wider comparators using modular IC blocks. So in summary, equality comparators detect matching bits using XNOR and AND logic, while magnitude comparators use hierarchical priority logic, and ICs like the 74HC85 implement this efficiently in hardware. Now let's introduce a very important digital block, the ALU, or Arithmetic Logic Unit. An ALU is a combinational circuit that performs one selected operation on two input values. Here, the main inputs are A and B, coming in through the input lines. At the top, we have an operation selector, also called the opcode. This opcode tells the ALU which function to execute. Inside the ALU, there are typically two major sections. First is the logic block, which performs operations like AND, OR, NOT, XOR. Second is the arithmetic block, which handles functions like addition, subtraction, and, in some designs, even multiplication or increment. Once the operation is selected, the ALU processes the inputs and generates the result on the output lines. So think of the ALU as a multifunction data path engine. It can add, subtract, perform bitwise logic, compare numbers, and even support shift operations depending on the opcode. This is why the ALU is called the heart of the CPU, because every calculation and decision eventually passes through this block. Let's look at a small ALU in a more engineering way by clearly defining its inputs, control signals, outputs, and flags. First, the inputs are two n-bit numbers, A n-1 to 0 and B n-1 to 0. So if n is 8, A and B are 8-bit values. Next is the control input, called the operation select, op k-1 to 0. This opcode chooses what the ALU should do, like add, sub, AND, OR, XOR, compare, or shift. Some ALUs also take an optional SIN, which is a carry-in used for add with carry, subtract, or chaining multiple ALU blocks. Now the main output is y n-1 to 0, which is the computed result. But a real ALU also generates important status flags. Count or borrow indicates carry out for addition or borrow for subtraction. 0 becomes 1 when the result is all zeros, very useful for equal checks. Carry, C, shows an unsigned overflow or carry condition. Overflow, V, indicates signed overflow. When the result exceeds signed range, and sign N is typically the MSB of the result, showing whether the signed result is negative. So, the ALU doesn't just compute a result. It also outputs flags that help the CPU make decisions like branch, compare, and error detection. Let's open the ALU and see what typical internal blocks exist inside a small ALU. First is the arithmetic block. This is usually built around an adder, and it can do both addition and subtraction. To subtract, the ALU commonly inverts B and sets sin equals 1, which implements 2's complement subtraction, A plus B plus 1. Next is the logic block, which performs bitwise operations like AND, OR, XOR, and NOT. These are fast, parallel operations done on every bit. Then we have the shift block. This can perform logical shifts or arithmetic shifts. And in more advanced ALUs, it uses a barrel shifter for multi-bit shifting in one step. After that comes the compare block. Comparisons like equality or magnitude are often implemented using a subtraction plus flags. For example, if A minus B results in 0, then A equals B, and the sign, carry, and overflow flags help decide greater than or less than. Finally, because multiple blocks can produce outputs at the same time, The ALU needs a final select stage. This is typically a MUX, controlled by the opcode, which selects the correct output and drives the final result Y. So the ALU is basically a set of specialized blocks running in parallel, and the opcode chooses which result becomes the final output. Let's zoom out and see how the ALU fits into a complete processor data path. At the top left, we have the register file. This stores operands and supplies input values to the ALU. Before entering the ALU, the operands pass through input muxes. These multiplexers select whether the ALU uses register data, immediate values, or other sources. On the right side, we have the immediate or constant unit, which provides fixed values for instructions like add immediate or load offsets. Inside the processor, the ALU performs the selected operation. An optional shifter may pre-process inputs or post-process results for shift instructions. The ALU then updates the flag register, storing 0, carry, overflow, and sign flags. These flags are critical for conditional branches. Below, the data memory interface connects the ALU to memory operations for load and store instructions. After computation, the result goes through a write-back or result MUX, which decides what value is written back into the register file. Finally, everything is orchestrated by the control unit, which generates control signals, selecting MUX paths, enabling writes, and choosing the ALU operation. So the ALU is not isolated. It sits at the center of a coordinated data path, working together with registers, memory, flags, and control logic to execute instructions. Now let's understand a powerful idea called LUT or ROM mapping. The key concept is simple. Any combinational logic is nothing but a truth table. A ROM or an FPGA LUT can store that truth table. Then your input bits act like an address. That address selects the correct stored output bits, exactly like a lookup. Now let's see ROM mapping. If you have n input bits, those n bits connect to the ROM address lines. That means the ROM must contain 2 to the power of 9 different addresses, or 2 to the 9 words, one for every possible input combination. Each stored word contains m output bits because your logic may produce multiple outputs. So effectively, a ROM can directly implement an n input, m output combinational function. Input becomes address, ROM data becomes the output. That's why ROMs and LUTs are so useful. Instead of building logic using many gates, you can implement the same function just by storing the truth table and reading it out. This is also the core reason FPGAs are flexible. Their LUTs behave like tiny ROMs that can be reprogrammed to realize any logic function. Let's make LUT or ROM mapping very concrete using 2 simple examples. Remember the rule. If you have n inputs, you need 2 to the power of n addresses in a ROM, because every input combination needs a stored output. Example 1. We have a 4-input logic block, A3 down to A0, and 3 outputs, Y2 to Y0. Since there are 4 inputs, the ROM depth becomes 2 to the 4th equals 16 addresses. And because there are 3 outputs, each address must store a 3-bit output pattern. So this function can be implemented as a 16 times 3 ROM. Inputs select the address, and the stored 3-bit word becomes the output. Example 2. Now consider a 9-input logic block, which means inputs A8 down to A0, and 8 outputs, Y7 to Y0. Here the ROM depth is 2 to the 9th equals 512 addresses, and each address stores 8 output bits. So the complete mapping becomes a 512 times 8 ROM. So the takeaway is, inputs decide ROM depth using 2 to the 9th, outputs decide ROM width using m bits, and the ROM or LUT becomes a direct hardware implementation of the truth table. Let's look at LUT mapping specifically in an FPGA environment. A LUT, or lookup table, is essentially a tiny ROM implemented using SRAM cells and a multiplexer tree. The SRAM bits store the truth table values, and the input signals act as select lines for the internal mux structure. So depending on the input combination, the correct stored bit is selected as the output. Common LUT sizes depend on the FPGA family. You'll typically see 4 LUTs or 6 LUTs in modern devices. A key rule is this: a K-input LUT can implement any K-input single-output Boolean function directly. For example, a 6 LUT can implement any 6-variable logic function without needing extra gates. If your design has multiple outputs, you either use multiple LUTs or, in some architectures, a wider LUT structure that supports multiple outputs. So in summary, an FPGA doesn't build logic from fixed gates. It programs LUTs which behave like configurable truth tables. That's what gives FPGAs their flexibility and reconfigurability. Now let's connect LUT or ROM mapping to classical logic design, specifically the decoder plus OR plane structure, also known as a PLA-style implementation. Conceptually, a ROM can be viewed as a decoder that activates exactly one address line, followed by an OR plane that generates the required output bits. When the input address is applied, the decoder selects one word line. The stored bits in that word then directly drive the outputs. So a ROM is essentially a hardware realization of a truth table using a decoder and programmable connections. Now look at the example shown here. We want to build a 1024 x 8-bit ROM, but we only have 256 x 8-bit ROM blocks available. First, notice that 1024 equals 2 to the 10th power, meaning we need 10 address bits. A 256-word ROM only supports 8 address bits, because 256 equals 2 to the 8th power. So what do? We use the lower 8 address bits to connect to all 4 256 x 8 ROM blocks in parallel. Then we take the upper 2 address bits and feed them into a 2 to 4 decoder. That decoder generates 4 chip enable signals. Each one activates exactly one of the 256 x 8 ROM blocks. So depending on the upper address bits, one ROM block is selected, and its 8-bit output becomes the final output. This is called ROM depth expansion. So the key idea is lower bits, internal address; higher bits, decoder for chip select. Multiple small ROMs combined into a larger ROM. This same concept is used in memory design, FPGA block RAM expansion, and even cache banking in processors. Where LUTs and ROM mapping are actually used in real systems. First, in FPGAs. LUTs are the fundamental logic resources inside an FPGA. Every combinational function you design is ultimately mapped into configurable LUTs, which behave like small programmable truth tables. Second, in microcontrollers and CPUs. Small ROM tables are commonly used for instruction decode logic, control signal generation, constant lookup tables, and even 7-segment display decoding. Instead of building complex gate logic, designers often store the mapping directly as a ROM table. Third, in ASIC designs, ROMs are used for fixed functions, especially when implementing dense, multi-output truth tables. For certain logic structures, a ROM-based approach can be more area efficient and structured than random gate-level synthesis. So, the core idea is this: whenever a function can be expressed as a truth table, it can be implemented either with gates or directly with a LUT or ROM. And that flexibility makes LUT-ROM mapping a powerful tool across FPGAs, CPUs, microcontrollers, and ASICs. Now let's discuss an important real-world issue in digital circuits: hazards, also called glitches. A glitch is a short, unwanted pulse that appears on the output, even though logically the final correct value should not change. Why does this happen? Because real logic gates are not ideal. They have propagation delay. When an input changes, different signal paths inside the circuit take different amounts of time to respond. If one path updates faster than another, there can be a brief moment where the output temporarily flips, before settling to its correct steady-state value. In the waveform shown here, input A changes at a certain time, but the output Y briefly drops, even though it should have remained high. This is called a static 1 hazard, because the output is supposed to stay at logic 1, but it momentarily glitches to 0. Glitches may look small, but in high-speed designs, they can cause serious problems, like false triggering, incorrect latching, or extra power consumption. So in practical design, engineers reduce hazards using proper logic minimization, adding redundant terms, using synchronous design techniques, or registering outputs with flip-flops. Understanding hazards is critical, especially in ASIC and high-speed FPGA designs. Now let's understand the root cause of glitches in combinational logic. A glitch occurs when an output depends on multiple signal paths from the same input, and those paths have different propagation delays. In real hardware, some paths are faster, some are slower. So when an input changes, signals do not arrive at the output at exactly the same time. During that transition window, one product term may turn off slightly before another turns on. Or in POS logic, one sum term may turn on before another turns off. Because of this mismatch, the output briefly changes incorrectly. Either it dips when it should stay high, or spikes when it should stay low. That temporary incorrect pulse is called a hazard. This issue is very common in SOP and POS implementations, MUX-based logic, decoder-style structures, and even LUT-based FPGA logic when not properly synchronized. The key takeaway is simple. Glitches are not logical errors. They are timing mismatches caused by unequal propagation delays in different paths. Now let's focus on the static 1 hazard. A static 1 hazard happens when the output is supposed to stay at logic 1, but due to unequal delays, it briefly goes 1, 0, 1. This type of hazard is most common in SOP form, that is, an OR of AND terms. Let's use the example shown here, y equals AB plus A prime C. Now assume the output is currently 1 and input A changes. Because signals travel through different logic paths, the two product terms don't switch at the same time. In a real circuit, it's possible that the term A prime C turns off first because A prime changes through an inverter path, and at the same time, the term AB hasn't turned on yet due to AND gate delay. For a brief moment, both terms become 0, so the OR output Y temporarily drops to 0, even though it should have stayed 1. That short, unwanted dip is the static 1 hazard. In practice, we eliminate static 1 hazards by adding a redundant or consensus term. So there is always at least one active path holding the output at 1 during transitions. Now let's read this waveform for a static 1 hazard using the function y equals AB plus A prime C. We are given B equals 1 and C equals 1 as constant highs, and only A changes from 0 to 1 at time t0. First, look at the logic before the transition. When A equals 0, then A prime equals 1, so A prime C equals 1. That makes Y equals 1, as expected. After the transition, when A equals 1, then AB equals 1, so again Y should be 1. So logically, Y must stay high the entire time. Now watch what happens in real hardware due to delay. At t0, A rises, but A prime doesn't fall immediately. It falls after the inverter delay, DINV. Then the A prime C path goes low after its own gate delay, so A prime C turns off at time t1. On the other side, AB does not turn on instantly either. Because the AB path has delay, AB becomes 1 later, at time t2. So between t1 and t2, both terms are temporarily 0. AB equals 0, A prime C equals 0. And because y is the OR of those terms, y briefly dips to 0, even though it should have stayed at 1. That short dip is the static 1 hazard, and the glitch width is the time gap. Glitch width equals t2 minus t1. So the key takeaway is static 1 hazards happen when one product term turns off slightly before the other turns on, due to unequal propagation delays. Now let's understand the static 0 hazard. A static 0 hazard occurs when the output is supposed to remain at logic 0, but due to unequal propagation delays, it briefly rises to 1 before settling back to 0. In other words, the expected behavior is 0, 0. But what actually happens is 0, 1, 0. This type of hazard typically appears in POS implementations, that is, circuits built as a product of sums. Why does this happen? When an input changes, different logic paths update at different speeds. One sum term may become high slightly before another sum term becomes low. For a short time, both sum terms are high. Since the final output is the AND of those sum terms, the output temporarily becomes high, even though logically it should have stayed low. That brief unwanted pulse is the static 0 hazard. So just like static 1 hazards cause unwanted dips, static 0 hazards cause unwanted spikes. Both are purely timing issues caused by unequal path delays. ... Now let's walk through this waveform example of a static 0 hazard. The function is y equals a plus b, a prime plus c. We are given b equals 0, c equals 0, and input a changes from 0 to 1 at time t0. First, check the logic. Before the transition, when a equals 0, a plus b equals 0, a prime plus c equals 1, so y equals 0. After the transition, when a equals 1, a plus b equals 1, a prime plus c equals 0, so again, y equals 0. So ideally, the output should remain low the entire time. Now, observe what happens in real hardware. At time t0, a rises. Because of propagation delay, the first OR term, a plus b, becomes 1 after its delay. The second OR term, a prime plus c, does not immediately become 0, because a prime must first pass through the inverter delay. So for a short time window, both OR terms are simultaneously high. Since the final output y is the AND of those two terms, y briefly becomes high, even though it should have stayed low. That temporary spike is the static 0 hazard. The glitch occurs between times t1 and t2, and the width of the glitch is glitch width equals t2 minus t1. After the slower path settles, one of the terms goes low, and y returns to 0. So the key idea is static 0 hazards happen when one sum term turns on slightly before the other turns off, creating a short, unwanted pulse to 1. Let's understand dynamic glitches, also called dynamic hazards. A dynamic hazard occurs when the output is supposed to change only once. For example, from 0 to 1 or from 1 to 0. But instead, it toggles multiple times before settling. So instead of a clean transition like 0 to 1, you might see 0 to 1, 0 to 1. This happens because different logic paths inside the circuit have different propagation delays. In multi-level combinational logic, meaning circuits with 2 or more gate levels, a single input change can split into multiple branches. Those branches reconverge later at the output. Because each branch has a different delay, the output may respond to one path first, then another, causing repeated temporary transitions. In the small diagram below, you can see Static hazards cause a single unwanted pulse. Dynamic hazards cause multiple pulses before the signal stabilizes. Dynamic hazards are most common in multi-level logic networks, MUX trees, decoder structures, large combinational data paths. The key idea is dynamic hazards are not logical mistakes. They are timing artifacts caused by reconvergent paths and unequal delays. Let's now understand why dynamic glitches occur. When an input changes, the signal does not travel through just one path inside the circuit. It splits and moves through multiple logic paths. For example, path A may have delay TA. Path B may have delay TB. If these delays are different, the signals will not reach the output at the same time. Now, if the output depends on both paths, meaning the logic reconverges, the output may temporarily evaluate to the wrong value. First, one path affects the output. Then another delayed path changes it again. Then yet another path corrects it. As a result, instead of switching once, the output may toggle multiple times before finally settling. That is the essence of a dynamic hazard. Now here's the key difference. In a static hazard, the output is supposed to stay constant, but briefly flips once. In a dynamic hazard, the output is supposed to flip once, but flips more than once. So dynamic hazards are essentially multiple glitch pulses caused by unequal multipath delays in multi-level logic. Now let's look at the classic conditions where dynamic hazards are most likely to appear. Dynamic hazards are typically seen in multi-level combinational logic, meaning circuits that have more than two gate levels. For example, consider an expression like A plus B, C plus D, and then that result feeds into additional logic gates. Because the signal passes through several stages, different paths accumulate different delays. Another common case is K-map optimized expressions. Even though the logic is minimized logically, the physical implementation may have uneven path depths. Some signals may pass through 2 gates, others through 3 or 4. That delay imbalance can create multiple transitions at the output. The third major cause is reconvergent fanout. This happens when a signal splits into multiple branches and later recombines. Since each branch has different delay, when they reconverge, the output may toggle multiple times. So the key idea is, dynamic hazards are not about incorrect logic. They are about multi-level logic depth and reconvergent paths, creating timing mismatches. That's why careful timing design and synchronous registration are critical in real ASIC and FPGA systems. Let's discuss how we reduce or eliminate hazards in combinational logic. First, we can add redundant or consensus terms. This is the classical method for removing static hazards. By adding overlapping implicants, we ensure that at least one logic path remains active during transitions. Second, implement the logic as proper two-level SOP or POS structures. Hazards are easier to analyze and eliminate in two-level logic compared to deep multi-level networks. Third, we can balance propagation delays, also called delay matching. If reconvergent paths have similar delays, the chances of glitches reduce significantly. Fourth, and this is the most practical solution, use synchronous design. By registering outputs with flip-flops, glitches are not captured since the system samples only at clock edges. Fifth, use hazard-free K-map grouping. When simplifying expressions, ensure adjacent ones or zeros are covered by common implicants to avoid static hazards. Sixth, use gray code in counters and FSMs. Gray code ensures only one bit changes at a time, reducing multi-bit transition hazards. Finally, for advanced systems, apply asynchronous design techniques carefully. using formal hazard-free logic methods. Now look at one of the most important techniques to eliminate hazards, adding redundant or consensus terms. Consider the SOP expression, F equals AB plus A prime C. This expression can produce a static 1 hazard when input A changes, because during the transition, one product term may turn off before the other turns on, causing a temporary glitch. To eliminate this hazard, we add the consensus term BC, so the hazard-free expression becomes F equals AB plus A prime C plus BC. Now, why does this work? The added term BC bridges the adjacent ones in the K-map. That means during the input transition, at least one product term remains high. So even if AB turns off momentarily and A prime C has not yet turned on, the BC term keeps the output equal to 1. In simple terms, the consensus term guarantees continuous logical coverage during transitions, so the output never glitches. This method is a classical hazard removal technique for SOP-based static 1 hazards. Let's look at the second method to reduce hazards, implementing logic as proper 2-level logic. Dynamic hazards usually occur in multi-level logic, where signals pass through 3 or more gate stages. For example, consider F equals A plus B A prime C. If this is implemented directly with multiple gate levels, the signal splits, recombines, and passes through uneven path depths. This creates different arrival times at the output, increasing the probability of dynamic hazards. So this is the bad implementation, a multi-level structure. A better approach is to convert the expression into a minimized 2-level SOP form using Boolean algebra or a K-map. 2-level implementations, meaning and/or or or-and structures, have more predictable timing and fewer reconvergent delay imbalances. As a result, the probability of dynamic hazards is significantly reduced. So the key idea is, the deeper the logic, the higher the hazard risk. Keeping logic in clean 2-level form improves timing behavior and stability. Now let's discuss the third method to reduce hazards, balancing propagation delays, also called delay matching. Hazards often occur when reconvergent paths exist. That means a signal splits into 2 or more branches and later recombines. If one path is faster than the other, the output may briefly evaluate incorrectly. To reduce this, we can, first, add buffers to the faster path so both paths take approximately the same time. Second, match gate types along both paths. If one path has more complex gates than the other, their delays will differ. Third, equalize fan-out loading. If one path drives many gates and the other drives fewer, their effective delays will be different. The goal is simple. Make the path delays approximately equal, so T-path 1 approximately T-path 2. When arrival times are aligned, the chance of temporary incorrect evaluation is reduced. This technique is commonly used in high-speed data path designs, asynchronous circuits, and critical timing paths in ASIC implementations. However, in large digital systems, delay matching alone is not always sufficient, which is why synchronous design is still the safest approach. Let's look at the most practical and widely used solution to handle hazards: synchronous design. In synchronous systems, we don't rely on raw combinational outputs directly. Instead, we register the output using flip-flops. So the structure becomes combinational logic, D flip-flops, next stage. Here's the key point. Even if glitches occur inside the combinational logic, that's usually okay, as long as the signals settle to the correct final value before the clock edge. The flip-flop samples only the stable value, so the flip-flop effectively acts like a filter. It ignores short pulses that happen between clock edges. That's why, in real-world ASIC and FPGA designs, hazards inside combinational logic rarely cause functional problems, because outputs are typically captured only at clock boundaries. So the takeaway is simple. If you design synchronously and meet setup, hold timing, glitches become an internal timing artifact, not a system-level bug. Let's talk about another very important technique, hazard-free K-map grouping. When we draw a Carnot map, our usual goal is to get the minimal expression. But minimal logic is not always hazard-free logic. For SOP implementations, we must make sure that all adjacent ones are covered properly. If two adjacent ones are not included in a common implicant, a transition between them can create a static one hazard. Sometimes we need to overlap groups intentionally. This overlap creates redundant coverage, which prevents uncovered transitions during input changes. Also, avoid grouping that is minimal only if it leaves transitions between adjacent cells unprotected. In other words, a slightly non-minimal expression may actually be the safer and more robust design. So the key idea is minimal logic reduces gates. Hazard-free logic ensures stable transitions. In real digital design, correctness and stability are more important than absolute minimal gate count. Now let's look at another practical way to reduce hazards using gray code, especially in counters and finite state machines. When multiple bits change at the same time, the probability of hazards increases. For example, in normal binary counting, 0, 1, 1 transitions to 1, 0, 0. Here, 3 bits change simultaneously. If those bits do not switch at exactly the same time, which is very common in real hardware, temporary intermediate states may appear. That increases glitch and hazard probability. Now, compare that with gray code. In gray code, only one bit changes at a time. For example, 0, 1, 0 transitions to 1, 1, 0. Only one bit changes. Because only a single bit transitions, there are fewer reconvergent timing mismatches. Finally, let's look at advanced techniques used in true asynchronous systems. In synchronous systems, the clock hides most glitches. But in asynchronous circuits, there is no global clock to mask hazards. So hazard-free behavior becomes absolutely critical. One important component used in asynchronous design is the Muller C element. The C element changes its output only when all inputs agree. If inputs differ, it holds the previous state. This naturally filters transient mismatches and prevents unwanted glitches. Another key technique is proper handshaking. Instead of relying on fixed timing, asynchronous systems use request-acknowledge protocols. Signals are accepted only after they are stable and acknowledged. In synchronous systems, the clock protects you. In asynchronous systems, the logic itself must be hazard-free by design. That's why asynchronous design requires deeper timing discipline and specialized techniques.